Good morning, everyone. My name is Joshua Carlson. My colleagues on this project are Justin Bentley, Andrew Sparrow, and Mike Fontaine, and we designed a variable buoyancy ocean profiler. Our sponsor was School of Marine Science and Technology, UMass Dartmouth, and faculty advisor was Dr. Goodman.
The scope of our project is to design and build a deep ocean profiler capable of diving to 1,000 meters. It must be deployed and retrievable by one person, autonomously operated, and capable of taking measurements of temperature and pressure. We were given a budget of $3,000, and we had to design and choose all components to withstand a minimum of 1400 psi, the operating pressure at 1,000 meters.
To distinguish our project from other devices that are out there, we decided to focus on a few particular attributes to design around. We chose cost to be the most important because what's already out there is very expensive, and with our budget being just a tiny fraction of the cost of one of these more professional devices, we decided that's what we'd focus on. We wanted something small as well to be deployed by a single person, retrieved by a single person, that also saves a lot of money in the long run, not having to rent a crane and boats every time. We ended up deciding that GPS and communication were just outside of our scope for this project. Didn't even focus on them. We had several options for our hull if we wanted it to be made of aluminum or something stronger like steel. We had to choose various shapes. I mean, something spherical has the benefit of being equally pressured on all sides, but very difficult to manufacture. And we had the option of several different O-rings, which was design as well. The buoyancy system, we had to choose between various working fluids such as compressed air or carbon dioxide if we wanted an oil bladder that would be inflated and deflated with buoyancy. And if we wanted the chamber exposed to the ocean or self-contained.
So the design we came up with, first of all, existing systems, the way they work is normally they're deployed from a large ship, and the instruments are attached to a cable and lowered with a crane, which is very expensive to do research because you have to either have a ship or have a ship, and it needs to be crewed. The other option is using an AUV, which is an autonomous underwater vehicle, and you also need a crane to deploy those, and they're also very expensive to purchase. So our goal was to make a product that was cheaper and easier to deploy. So the solution we came up with is a open buoyancy chamber compressed gas system. So the way it works is three separate parts. There's an open buoyancy chamber, which is exposed on both sides to the pressure of the ocean. There's a pressure housing which protects the microcontroller, the batteries, and all of the electronics from the ocean water. And there's also a compressed gas system which uses compressed gas controlled by a solenoid to modify the buoyancy once it's ready to surface. So this is a cross-section of our device, and as you can see, we have the compressed gas system attached to a high-pressure solenoid, which then is released back into the open buoyancy chamber. That's controlled by a microcontroller, and then our batteries, and then we have a temperature and pressure sensor at the bottom. This is a breakdown of how our compressed gas system works. So we have a 3,000 psi tank regulated down to 2,000 psi, a shut-off valve, which is connected to high-pressure hosing into the high-pressure solenoid, back out through a check valve, and back into the buoyancy chamber. So the way our device is designed to operate is when it's on the surface, the microcontroller goes into dive mode. So when it's in dive mode, there's a solenoid at the top of the buoyancy chamber, and that solenoid is open, allowing the air in the buoyancy chamber to leave and flooding it. As it floods, that decreases its buoyancy, and eventually the device will begin to sink. Once the microcontroller senses that it's sinking, it goes into sink mode, where it closes out the microcontroller so that it has a steady dive, and then senses, am I diving, am I diving, am I diving, and if it's still diving, it continues in the dive mode. Once it reaches the maximum depth that it's programmed to reach, it goes into surfacing mode, where it will open up the high pressure solenoid inside the chamber, and this high pressure solenoid releases gas through the high pressure lines into the buoyancy chamber. And it will do that in 1 second pulses. And it will keep doing that until the microcontroller senses that it's rising, and then it goes into rise mode, sensing, am I rising, until it reaches the surface. It also has a fail-safe mode, so if it's not receiving depth readings or pressure readings, after a certain amount of time, it will open the high pressure solenoid and just flood the tank to do like an emergency blow or like a submarine. So what I'm going to show you now is a video of one of the tests. So what you're going to see here is a device that the top solenoid is open and it's flooding the chamber and it's beginning to dive, and it's going to dive to a certain depth. And once it's at that depth, it will activate its buoyancy system. This is an underwater shot. The device is in the center, it's a little hard to see. So the buoyancy system is activated, and it's on the surface.
The buoyancy calculations were very helpful in designing the buoyancy chamber. The mass of the pressure vessel and all the components we actually had to approximate because we didn't have these items when the buoyancy chamber was constructed. The density of the device minus the buoyancy chamber is determined by dividing the total mass of the device by the total mass on. This yielded specific gravity of 2. We wanted to know how much additional volume was required to create natural buoyancy or neutral buoyancy in the water with our device. We did this by setting the device the density of our device equal to the density of our water. We calculated the minimum diameter of the buoyancy chamber. The buoyancy chamber is spherical, so we wanted to find the smallest diameter possible to actually keep it afloat. We came up with about 11 inches, and so knowing that it's 11 inches for the minimum diameter, we went and made about 14 inches in diameter for our actual buoyancy chamber, just as a fail-safe.
This is the second half of the calculation is just stuff like that. So minimum diameter is 10 inches for that sphere. To make sure that the device could withhold or withstand 1,000 psi, 1,000 meters of pressure, which is 1,400 psi, we did finite element analysis. So this is a full 3D rendering of our model, which we imported into ANSYS from SolidWorks, created a volume meshed it. We fixed the bolts and fixed one side of the device. The inside was set to 1 atmosphere of pressure, and the outside to 3,000 psi. And what we found was stress concentrations was a bearing stress around the bolts, and we had a factor of safety of greater than 2 based on this. We also, to double check that, we did axisymmetric model, which is this one section of the wall, and we came out to very similar numbers. We did the end caps. So this is an axisymmetric model of the end cap, and we found the stress concentration right with a flange and the wall that changed in geometry. So because of that, we modified our design and added a fillet to the inside and outside of the flange. And this is a full 3D rendering of the end cap also. And then the seal each end cap, we used a 1/16 O-ring, which was 5 inches in diameter, and 10 3/16 stainless steel bolts and washers. We, because the pressure housing was too large to really machine on campus, we had to outsource that and the end caps to a machining company.
The buoyancy chamber, we constructed a general all-purpose fiberglass. We actually bought fiberglass at Home Depot, that's how general it is. We use fiberglass because it's cheap, it's pretty easy to work with, and it has a very high strength to weight ratio. As you can see, a mold in the back, it was not very, but that's a plaster mold that we use to create the two halves of the fiberglass mold for the buoyancy chamber, and we actually connected those with fiberglass. And we sanded it and put some epoxy-based marine paint on it. We chose a very bright, this is after the sanding, and we actually used a very bright red color to make sure we can see it when it's deployed in the water.
We ran several tests for our device. The earliest tests were just to make sure that the pressure pump was actually watertight, so we just deployed it into the water, let it sink for a while, let it stay on the bottom for several minutes, and then pull it back up, open it up, and see if we had any water inside. We also tested it with the buoyancy bell on top of it to make sure that it would, well, to see how well it would be buoyant. We found out that it was actually very positively buoyant, again, because of the extra diameter added to the buoyancy bell. We also assembled the prototype and tested full functionality with the microcontroller controlling both of the solenoids. That was shortly after testing the circuitry itself, which was done with first a variable voltage provider, and then, yeah, this is some of the programming output. But we tested with a variable voltage provider to simulate the sensor input, and then tested with the actual sensor input to make sure the relays and solenoids being able to this is just some of the debug information from the program while it was still connected to and communicating with the computer. This is just as I myself was changing the input voltage, simulating the sensor input, watching the debug information, make sure that the program recognized the input, recorded it as a pressure, recorded the temperature, was interpreting the voltages with the right calibration, and was responding properly by changing modes and finding the correct solenoids. Again, as was said earlier, our device is a lot less expensive than devices that are currently available. Some of the devices from Web Research are well over $50,000. They are much larger, require a crane to drop into the water, require a crane to retrieve, and require a much larger boat for all of those accommodations. Our system does not require a crane, it can just be literally tossed in the water by one person, it can be hauled up by one, possibly two if it's still carrying a lot of water, but certainly not within the range of a crane, and that means that doesn't mean as big of a boat to come in the crane. This is just an analysis of our budget. Solenoids turned out to be very expensive because of the high pressures that we were working with. Microcontroller was actually quite inexpensive, bought from an Italian company with open source programming language. Temperature sensor, pressure sensor, again, a little bit expensive because it goes down to 2,000 psi. And the supplies for the pressure pump as well were designed to withstand that pressure and much more in factor of safety.
As engineering students, it's important for us to make sure that we were acting ethical throughout our project, and we feel safe to say that we were. This really has a negligible effect on the general public. We were honest with our client, which is always important. We gave credit where it was due. However, us being 4 mechanical engineering students and this requiring fairly extensive electrical engineering knowledge, we had to work a bit outside of our expertise. It was a learning experience, but it worked out for the most part. In the environment, we feel that there's nothing hazardous really about our project. I mean, it's using air, which is completely safe. It's all self-contained. There's no debris. It's got a good structure to it. The alkali batteries don't count as some states consider that to be a waste. Federally, they do not consider it. And it has very high efficiency, very low power usage. Are there any questions?